In previous lecture, I already discussed type of simple graph like complete graph, cycle, wheel, bipartite graph, complete bipartite graph. Today I will discuss some examples. Now theorem 5, biparative graph have no cycle of odd length. There can be cycle of even length, but there are no cycle of odd length. Just for example, suppose A, B, C is in one group, 1, 2, 3 is in another group. There is a edge from A to 2, B to 2. There is a edge from A to 1, B to 1. And there is a edge from C to 3. So now this A1, B2 is creating a cycle. So from A to 1, then 1 to B, then B to 2, 2 to 1. This is a cycle. So you can write A1, B2. A to 1, then 1 to B, B to 2, 2 to A. This is a cycle of length 4. And 4 is a even number. So there can be no cycle of odd length. Let this is A, B, C, 1, 2, 3. So there can't be cycle of length 3 like A to 2, then 2 to B, B to A. This cycle is not possible. This is a odd length cycle. So biparative graph have no cycle of odd length. There can be cycle of even length, and maximum number of edges possible in a bipartite graph is n square divided 4 float function. Now let's see one example. Example 5, in a graph G, n equals to 10, then maximum number of edges possible equals to 10 square divided 4. 10 square divided 4 is 25. So total vertex equals to 10. We can do partition like 5, 5. When both side 5, 5, so there are 25 edges, 5 into 5. When one side is 6, another side is 4, there are 24 edges. When one side is 7, another side is 3, there are 21 edges. When one subset contains 8, other subset contains 2, there are 16 edges. So maximum number of edges is 25. Next, cyclic graph. A graph having at least one cycle is called as cyclic graph. Cycle graph and cyclic graph both are different. Cycle graph means the graph total is a cycle. This is a cycle, okay? But a graph having at least one cycle called as cyclic graph. Suppose this is a cyclic graph. Here there is one cycle of length 3. The total is not a cycle, but if it contains at least one cycle, then it's a cyclic graph. If it doesn't contain at least one cycle, then it is a acyclic graph. So a graph with no cycle called as acyclic graph, and a graph with at least one cycle called as cyclic graph. There can be multiple cycle also. So this is a graph having 1, 2 and whole is 1. So there are 3 cycles. Tree is a connected acyclic graph. Means there should not be cycle in tree, and a tree with n vertices have n minus 1 edges. Next, complement of graph. If there is a edge present in the graph, then in complement there will be no edge. Okay, it's just reverse. So let G be a simple graph with n vertices. The complement of G denoted by G complement is a simple graph with same number of vertices as that of G, but 2 vertices U and V are adjacent in G complement if and only if they are not adjacent in G. Suppose this is a graph, then its complement will be this. So the edges which are not present in this graph are present in its complement. And graph plus its complement, number of edges will be equals to complete graph number of edges. So E of G plus E of G complement equals to E of K of N. K of N is for complete graph. So total number of edges in complete graph is sum of graph edges and its complement. Now let's see one example. Example 6. Let G is a simple graph with 10 vertices and 18 edges. Find the number of edges in G complement. So there are 10 vertices and 18 edges. So number of edges in graph is 18. 18 plus its complement edges equals to 10 vertices. So 10 multiplication 9 divide 2. N into n minus 1 divide 2. So 10 divide 2, it will be 5. So 18 plus number of edges in that complement graph equals to 45. So G complement edges will be 45 minus 18. It's 27. So answer will be 27. 27 plus 18 equals to 45. Now another example, example 7. Let G is a simple graph with 24 edges and G complement has 54 edges. Find the number of vertices. We need to find number of vertices. We have edges of the graph and its complement. So 24 plus 54 equals to n into n minus 1 divide 2. This n is number of vertices. Now we need to find this n value. So 24 plus 54, it's 78. So 78 equals to n into n minus 1 divide 2. So now n into n minus 1 will be 78 multiplication 2. So 78 multiplication 2, it's 156. Now n into n minus 1 is 156. So 13 into 12 equals to 156. This is our n, this is our n minus 1. Hence n value is 13. Let's see one more example. Example 8. We have 24 edges. Degree of each vertex equals to k. Which of the following is possible number of vertices in a simple graph? So we know the formula that sum of degree of vertex equals to 2 into number of edges. So n into k equals to 2 into number of edges, and edges given is 24. So 2 into 24 equals to 48. So n into k equals to 48. Suppose k equals to 1, n can be 48. Suppose k equals to 2, n can be 24. If k equals to 3, means degree of each vertex is 3, n can be 16, there can be 16 vertex. If k equals to 4, n can be 12. If k equals to 6, n can be 8. Now check the option. Here 16 is present, n 16 is possible. So here answer will be 16. So there can be 16 vertices. So number of vertices equals to 16, and each vertex can have degree 3. So if each vertex equals to degree 3, then 16 into 3 equals to 2 into number of edges, that is 24. So both are 48. Next, example 9. Maximum number of vertices possible in a simple graph with 35 edges and degree of each vertex is at least 3. It is asking maximum number of vertices possible. So 3 into number of vertices is less than equals to 2 into 35. So B can be less than 70 by 3, it's 23. Next, example 10. Which of the following degree sequence represent a simple undirected graph? So some degree sequence are given. From the degree sequence we need to identify whether it's a degree sequence of simple graph or not. First, option A, 2, 3, 3, 4, 4, 5. This is not a simple graph degree sequence, as there are degree like 3, 3, 5. There are 3 vertices of odd degree. In case of simple graph, there can be even number of vertices having odd degree. Here 3 vertices having odd degree, hence this is not a simple graph. Next, option B, 2, 3, 4, 4, 5. There are 5 vertex and maximum degree is given 5. This is not possible. If number of vertex equals to 5, then maximum degree should be 4. Hence, option B is also not a simple graph degree sequence. Next, option C, 1, 3, 3, 4, 5, 6, 6. So there are 7 vertices and maximum degree is 6. So 2 vertices having degree 6 means minimum degree should be 2. So degree 1 is not possible. So minimum degree should be 2. Hence this is not a simple graph. Next option D, 0, 1, 2, 3 till n minus 1. In a simple graph, if there are n vertices, maximum degree will be n minus 1. N minus 1 means that is adjacent with all other vertex. So degree 0 is not possible. Minimum degree can be 1. Hence this is also not a simple graph. So identifying simple graph from the degree sequence is difficult. We need to check whether there are even vertices having odd degree, whether this is possible or not. There are too many things and it's difficult. So better we can use the Havel-Hakimi algorithm. This algorithm is used to identify a degree sequence is a simple graph degree sequence or not. So what is the algorithm? We have a degree sequence in the decreasing order. So what we will do, every time we will remove one vertex and all its adjacent edges. D1 we are removing, so D2 onward we will subtract 1, and for how many vertex we will do? For D1 vertex we will do. Through an example you will understand better. Suppose this is a graph, let A, B, C, D. Here each vertex have degree 3. So A vertex is degree 3, B vertex is degree 3, C vertex is degree 3, D vertex is degree 3. So all vertex have same degree, we can write in any sequence. Always we need to write in decreasing order. If all are equal, you can write in any sequence. So first we will remove A. We'll remove A and all its adjacent edges. So after removal of A and all its adjacent edges, now degree of B is 2, degree of C is 2, degree of D is 2. We removed A and all its adjacent edges. Next we will remove B and all its adjacent edges. So after removal we will just get CD. So now degree of C is 1, degree of D is 1, and this is possible. Okay, so this CD is a simple graph. We just need to check, is this a simple graph? Yes, this is a simple graph. There are no multi-edge, there are no self-loop. So this sequence 3, 3, 3, 3 is a simple graph degree sequence. And sometime during the process we may get a non-decreasing sequence. First we need to arrange in decreasing sequence, then we can apply the algorithm. Now example 11, we have a sequence 6, 6, 6, 6. There are 4, 6, 4, 3, 3, 0. So first we will remove 6. Now next 6 vertex degree will be decreased. So 6 will be 5, then next 6 will be 5, this 6 will be 5, 4 will be 3, 3 will be 2, 3 will be 2. Next we will remove this 5, means we are removing that vertex having 5 adjacent. So next 5 vertex degree will decrease 1. So it will be 4, 4, 2, 1, 1, and this 0 is given before. Next we will remove this vertex. So next 4 vertex degree decrease by 1. So it will be 3, 1, 0, 0, 0. So now this is not possible. This is not possible of a simple graph. Like one vertex have 3 adjacent. Let this is A, and another vertex have degree 1. Then there are 3 vertex having degree 0. So what's about these 2, right? So this sequence is not possible for a simple graph. Hence this whole sequence is not a sequence of a simple graph. As the last result cannot represent by simple graph, hence the sequence is not a simple graph. Let's see another example. 6, 5, 5, 4, 3, 3, 2, 2, 2. So first we will remove 6. So next 6 vertex degree will be decreased by 1. So this 5 will change to 4, then 5 will change to 4, 4 will change to 3, 3 will change to 2, 3 will change to 2, this 2 will change to 1, then 2, 2. Now this is not in decreasing order, so we need to arrange it in decreasing order. So these 6 vertex will decrease by 1. After decrease, as this is not in decreasing sequence, so we arrange in decreasing sequence. Next we'll remove this degree 4. So next 4 vertex degree will decrease by 1. So this 4 will be 3, this 3 will be 2, this 2 will be 1, this 2 will be 1. So 3, 2, 1, 1, 2, 2, 1. This sequence is again in non-decreasing order. So first arrange in decreasing order. Next we'll remove this degree 3. So next 3 vertex like these 2 value will change to 1. 1, 1. So finally we got 1, 1, 1, 1, 1, 1. Is this possible for a simple graph? Let me take 6 vertex A, B, C, D, E, F. We have 6 vertex. Now A degree is 1, B degree is 1. Then C, D both degree are 1. F, E both degree are 1. This is a simple graph. All degree are 1. As for this sequence, simple graph possible. Hence 6, 5, 5, 4, 3, 3, 2, 2, 2 is a degree sequence of a simple graph. So this graph is not connected, but it's a simple graph. In next lecture, I will discuss bipartite graph and matching. If this lecture is helpful for you, please like, share and subscribe. Thank you.